Well, hello students. We're starting the Chapter 4 lecture series here, and we're getting into forces and Newton's laws of motion. So we're going to establish a connection between chapters 1 and 3 and our study of motion. And now we're going to introduce the why of why something's moving. So as you recall, motion, the study of just motion is kinematics, and now we're introducing dynamics, which we'll look at the forces that cause motion. This here is just a summary of what I just mentioned in the slide before. So motion, it doesn't have, Galileo said, okay, we don't need to have a cause for their motion. This is pretty insightful, so you can start studying motion without necessarily worrying about the cause of it, which is going to be a force. Forces are pushes or pulls, but we end up categorizing them with more detail as we look at different scenarios. It helps us organize and figure things out. But if you sat there and you thought to yourself, gosh, it's a push or a pull, and you would be right, but we get these pushes and pulls and we give them more detailed labels. So we're going to look at important forces. Weight is very important. We're very familiar with this. It's the force of gravity acting on objects. So we experience this on our spring force. And a normal force is a supportive force that a surface it exerts on an object. We usually look at a book on a desk. I like this example here with the young lady leaning on the wall because the wall is a supportive force. If that wall wasn't there, she would fall sideways. So let's move on. Free body diagrams are big, and we're learning how to do this and practice this in class. So you have to be informed of what the object is. In this case, the object is this, this person hanging from this rope. And we circle the object of interest to isolate it from the surroundings. And then we focus on, okay, what's touching the object? There's touching right there. And then there's your tension of the rope from the touching. And of course, this is our long range or non-contact force, the weight of gravity. So this is a proper free body diagram here. It's in equilibrium. Forces going up vertically equal the forces going down vertically. So what causes motion? Objects like this with smooth snow, this is going to slow down, and most of y'all, yeah, because there's friction. You're already aware pretty much of friction in your life. If you have slick ice, this would be more like your hockey players on ice. You go further because the friction is less. And then a frictionless surface with a lot of problems will do frictionless, so you can learn what's going on here. You can see the sled never stops. If you use your point particle methods, you can see that this continues on moving. This one here you see is slowing down over a little more time, and then this is slowing down quickly. So you could put a point in the middle of each of these, the child at each time frame. Newton's first law states that if there's no outside force acting on an object, if it's at rest, it's going to stay at rest. If it's moving, it's going to keep moving in a straight line at whatever speed it has that it's moving at. So this particular picture here is showing this body, this crash dummy, and the green vector is velocity. If this crash dummy didn't run into anything, it would just keep cruising along at this particular velocity. So, but the fact is that it does run into something. It runs into the front of the car, the steering wheel, and you can see at each successive frame that the velocity does change. And because there is an outside force acting on the crash dummy, so the crash dummies are an object of interest, and it's the car, the front of the car to be exact. So let's look at what we consider forces. A push or pull. We talked about agent-object notation. The agent is the dealer, the object is the feeler. And the object, when we do free body diagrams, will be the point of interest. It's a vector, so we'll use, you'll notice in this PowerPoint program that that force vectors are red. And we can categorize forces into contact force, involves touching, and long-range force. It's not touching, so gravity is the one we'll be looking at. Electromagnetism, electricity, and magnetism are also long-range forces. We will not be looking at those. Here's a force vector. This is a proper force vector. We represent objects as point particles. And whenever you draw the force or forces that are acting on that object, the tail of the vector needs to go on the point particle. And also there should be an appropriate label. So here is the catalog of forces. I'm going to move through these quickly. You're welcome to pause it if necessary. It doesn't matter where this ball is in the air. We still have the weight of gravity on it. Students see the ball moving horizontally and they want to put a force vector on here like there's something going on. There's nothing going on in the air except for gravity. So this is appropriate free body diagram for each of these balls except for these two here. There you would have a normal heading up on it. But in the air here, I really like this. No matter where it is in its flight, the force vector is heading down for weight. This is the force of a spring. So for this one here, the spring is exerting a force on the box. It's heading to the right. And then here you see it's pulling the box back. So that we use SP for spring. Tension is for ropes, chains, that sort of thing. You're going to see a lot of ropes. So on the sled, this represents a sled, and there's your tension force. There's other forces that are acting on this sled, but we're going to ignore those for now since we're just introducing the catalog of forces that you'll be using. Normal force, like we said before, is a supportive force, and I like this. This is what's kind of going on the molecular level. And I also like the textbook mentions that it's not really molecular springs. It acts like molecular springs, but these springs are more of electromagnetic force or electric force occurring within the atoms that make up a particular material, like a wall or a desk. Friction. There's two types of friction, kinetic and static. Kinetic is the moving friction. And what happens is you have an object moving to the right. Friction always opposes motion. So when you do diagrams, free body diagrams, you'll always have the force vectors, friction force vectors, opposite of motion. Notice over here that it says, well, gosh, this kid's moving. So yeah, I know this is opposite of motion. So what do we do? How do we know the direction for the static one, the static friction one? So let's take a look at this frog here sitting on the ramp. So obviously this frog's not moving. So instead it's not sliding down the hill. So some force is keeping it on this downhill slope, not sliding down. So it's friction. So what we do is to take care of this, we say friction, kinetic friction opposes motion. Static friction opposes impending motion. You're like, impending motion, what does that mean? If the frog was going to slide, that would be here. So that's kind of what we mean by impending motion. So if the frog's going to slide anywhere, he's going to slide down this way, or she, who knows what this frog is. So what you're going to do is you look at the static friction force vector and you draw it opposite of which way the frog would slide if it could slide. And that's what we mean by impending motion. All right, drag is a contact force. And because it's in contact with air molecules, you've probably seen leaves fall slowly from trees. And then if anything else, like an acorn falls, that falls quickly. So you know that there are forces going on with drag that affect how it falls to the ground. You've probably seen this if you've dropped a piece of paper in the classroom versus a pencil. So the drag force varies, and we'll be taking a closer look at that. So that's our drag force. It's a type of friction force. Over here we have a thrust force. And for this one here, this is the rocket is being pushed by exhaust gases. There's also a thrust force. If you see an airplane in the air, we call that thrust. Let's say an airplane's heading to the right. So we end up having gas exhaust, and it's pushing the rocket up. And let's say we had a plane heading to the right, it would head it to the right. So we call this a thrust force. So identifying forces, take a moment and pause this and take a look for yourself. This is how you do it. Let's look at two conditions for equilibrium. And this matters that you know something is in equilibrium. So there's static equilibrium and dynamic. Static equilibrium is an object is not in motion, it's at rest. Dynamic equilibrium, the object is in motion at constant velocity. Let's look at examples. Static equilibrium. Here they are. Take a moment, pause it. Dynamic equilibrium. Here are some examples. Pause it. Take a moment to look through them. So let's get to our first example problem. So we're going to start all the problems we're looking at in this slideshow. We're going to stick with constant velocity, or they're at rest. So that means they are in equilibrium. So you want to say to yourself, is it static equilibrium or is it dynamic equilibrium? So if the object's at rest, and that means it's static. If it's at constant velocity, that means it's dynamic equilibrium. All right, so you're going to try this one first by drawing a picture of the block being dragged uphill by a rope. And then you're going to use the technique we learned in class to see if you can draw a free body diagram for this. So here's my drawing. If you notice, I drew my picture. I drew the little dotted line around the object of interest, which is the block. I put X's where the outside environment is touching our object. So the hill's touching, the rope's touching. Over here, I have the tension force, the normal force, and the friction force. Long-range force is gravity. So these are my touching contact forces. This is my long-range force. So this is the start of you determining how to draw a free body diagram. So you want to pause it, try to draw the free body diagram yourself, and then move on to the next slide when you're ready. So here's the drawing. So tension, the rope is pulling up the ramp. The normal force is a supportive force being exerted, by the hill. The frictional force is kinetic because it's at constant velocity. That means it's dynamic, it's moving. So we have a frictional force in the opposite direction, in the opposite direction of motion. And then last but not least, we have the force of gravity heading down. You've noticed I tried my best to have the forces equal each other. My gravitational force vector here is probably too long, because if you took this y component going up and the component of this one, this y one going down, and then you subtracted this one going down here, the y component heading down, I have way too much gravity going on here. I probably need to shorten this a little bit. So we do our best to try to make our force vectors the length they should be. And since this system is in equilibrium, the x components, positive x components should equal the negative x components. The positive y components should equal the negative y components. So we did our best. I did my best here. So in class and in your practice at night, you'll try to do your best as well. Let's try another one. So pause this and you can click onto the next screen. What you're doing is you're drawing a picture first, circling it using the dotted line, finding the contact and non-contact or long-range forces, and then finally drawing that free body diagram. So here's my drawing. Here's A, and hanging from it is B. I did the little schema circle around it, the dotted line to see what's touching it. You'll notice something's been added. There's two ropes, so now you have to identify the rope by labeling rope 1, rope 2. Those are my contact forces because they're touching block A, and then I have a long-range force of gravity at work. So let's go ahead and move on to seeing how the free body diagram looks. So this is new to you. The tension 1 going up and the tension 2 going down, that was no surprise to you. And you probably thought to yourself, gravity is also affecting block A. Where in the heck do I put that force vector? There's not a lot of room there. What do I do with that? Do I lay them on top of each other? You can lay them on top of each other and label them as long as you have a T2 and a G labeled. You can also do this technique here. Physicists know this is used so you can see multiple forces that are in the same dimension. So this is fine and this is acceptable. All right, let's try this ball hanging from the ceiling. Hit pause. You're going to draw a picture and you're going to try a free body diagram and then see what you got. So here's the picture. First, you have to realize it's after it releases. So snap, boop. So this is what you have after the rope breaks. Here is the ball. So go ahead and try to do your free body diagram for the ball right here at this moment when it's in the air. This is what I got. So this is the free body diagram. There's only gravity working on it. Nothing is touching the ball after the release. So students make a big mistake here, and they like to put forces on here that don't exist. Okay, you don't want to be one of those students. Be very careful. Draw the object, put the circle, the dotted lines around it to see what is touching your object. There's nothing touching this object. So this is the answer. So that last example, like Miss Eisenhower, that wasn't in equilibrium. It was accelerating towards the ground. Yeah, you're right. It's like a little tickler there. So we'll get to that when we look at Newton's second law. But we're back to equilibrium here, and this is going to be dynamic equilibrium because it's at constant velocity. So you try this one yourself, hit pause, and see what the answer is. So here's my rope, my bucket. It's constant velocity, so it's dynamic equilibrium. And let's get to the answer. I hope you're doing this on your own and not just looking at my answers. All right, so we have tension from the rope. Then we have gravity heading down. You're like, Miss Eisenhower, you didn't do the circle around it like you usually do. You're going to get to the point where you are so used to doing these diagrams. You need to use the dotted line around the object of interest when they're complex or when you're learning it. And right now you're learning it, so you want to use that technique until you feel comfortable that you definitely know your stuff. All right, this is the last one we're going to practice here. Pause it and give it a whirl. This is the airplane flying. Here's my drawing. So you're like, hey, Miss Eisenhower, it's dynamic equilibrium, and I know gravity's working, and I know we have drag here on the plane. I've seen drag in action when I drop paper in the classroom. We talked about thrust earlier in the, or you did earlier in this lecture by having a drawing. There was a rocket heading up. So what's this lift about? So let's see. I'm going to go to the next slide here. This is what lift is about. So thrust pushes the plane forward. Drag is friction, and it opposes motion. You're like, okay, drag is a type of friction, it opposes motion. Gravity's heading down. So what is helping this airplane heading up? It's called lift. And this is a subject that you would study in fluid mechanics, looking at how the air passes over what's called the airfoil of the plane. And the differences in pressure or the air help lift it. So we don't need to know that. You don't need to know that. But you, when you look at this, you need to be aware that lift helps hold the plane up in the air as it travels through. And you're like, okay, I think I can do that. So this is Newton's first law here. Objects will move at constant velocity or remain at rest unless acted on by an outside force. So this is showing no forces, and then we're getting into, oh, if there's no forces, there's no acceleration. Okay, and that's the end of this slideshow.